Alright everyone, so thanks for coming along. My name is Anna, and over the last 2 months I've been working on the development of a beam centering controller prototype for the Adaptive Optics Demonstrator for tracking space debris, which is a project being jointly developed here at Mount Stromlo by EOS Space Systems and the RSAA, and I've been under the supervision of Dr. Francis Bennett. Alright, so the Adaptive Optics Demonstrator for tracking space debris, also known as the AOD, uses laser ranging technology to track space debris in low Earth orbit. This is in the hopes of providing vital information to satellite providers, which could be used in the future to help avoid potentially disastrous collisions between space debris and satellites. However, when we want to propagate any sort of light through the atmosphere, atmospheric turbulence poses a major problem. As the astronomers in the audience probably know, when wavefronts from distant objects such as galaxies propagate through the atmosphere, they become distorted. This leads to great difficulties in imaging. In this application, atmospheric turbulence leads to beam spread and wander in the probing laser beam, thus leading to a loss in tracking precision and accuracy. Adaptive optics systems are typically used to correct the atmospheric distortions by measuring the shape of incoming distorted wavefronts. This is a very simplified diagram of the adaptive optics systems that might be used in an instrument such as a telescope to correct the images of objects such as galaxies. A deformable mirror is used to correct the shape of this distorted incoming wavefront, thus resulting in nice, smooth, flat wavefronts. In the AOD, adaptive optics is instead used to correct the laser beam before it propagates through the atmosphere. It does this by reflecting the uncorrected wavefront off a deformable mirror, or a DM, it's a bit of a mouthful, such that when the laser beam passes through the atmosphere, the effect of the atmospheric turbulence is to remove the distortion that has been applied, thereby minimizing the spread and wander in the beam. However, in order to be able to apply this correction to the laser beam, the adaptive optics needs to obtain a reference for the distortion. This is achieved in AOD by using something called a laser guide star. A laser guide star is an artificial star which is created by propagating a powerful laser beam at 589 nanometers into the atmosphere. This causes sodium atoms in the mesosphere to fluoresce, which creates a bright, point-like light bulb. The wavefront sensor in an adaptive optics system will use the light from this light source to obtain the shape of the distortion of the wavefront, and then this information is used to correct the upgoing laser beam. So this is a diagram, this is the CAD model of the 1.8 meter telescope, which comprises the AOD. The probing laser is launched from the main telescope, the 1.8 meter diameter telescope, which is actually stuck on the hill over there. Whereas the guide star laser is launched off-axis from a much smaller telescope, which I don't think you can see on this diagram. And the laser itself is mounted on these blocks over here next to the person. And also on these blocks are some optics which are used to guide the laser into the laser launch telescope. So this is a close-up of the laser and beam transfer optics, and this is the laser launch telescope, which is used to aim the laser guide star into the correct part of the sky. So this very complex looking diagram is a diagram of the transfer optics which are used to aim and focus the guide star laser beam. The large number of optical elements in this system mean that there are many degrees of freedom. And factors such as temperature and the fact that the telescope has to move quite fast in azimuth and elevation as it's tracking an object in low Earth orbit means that these components are all prone to flex. This is a problem because it causes the laser beam to wander as it propagates through all these optics. And it is crucial that the laser beam always remains correctly aligned on the beam pointing mirror, or BPM, this component here, as this is what ensures that the laser beam is aimed towards the correct part of the sky. This is where my work comes in. So over the last 2 months, I've been working on the development of this beam centering wheel here, which is used to ensure correct alignment of the laser beam on the BPM. It consists of essentially 3 components. We have a computer to implement the control system. We have a beam centering loop camera, which images scattered light from the surface of the beam pointing mirror in order to provide feedback information on its alignment. The actuator in the system is the beam centering mirror, or BCM over here, which is continually controlled in order to correct the alignment of the laser beam. So for the prototype, this is a simplified setup that I used. So I didn't use a laser beam because there was no real need to, and it was unnecessarily dangerous. So I instead used an LED light source, and I simulated the beam by collimating it using a lens. And I decided to omit all of the optical elements in between the BCM and the BPM because they weren't required for the proof of concept design. However, I did try to make sure that the distance between these 2 meters was consistent with that in the final design, just for consistency. And the camera was simply an image sensor placed behind another focusing lens in order to focus the image of the beam pointing mirror. So these are some images of the setup that I used in the lab. So everything was done on an optical bench in one of the Adaptive Optics labs in the AITP. So here's my guide star laser. So I have the LED light source there and the collimating lens here. And here I have the beam centering mirror, a stop, and a folding mirror. And this is the camera, this is the imaging, so you can just see the lens in front of it. And this is the beam pointing mirror. So I didn't actually use a moving mirror for this part because it wasn't necessary. And also to increase the light reflected in the surface of the camera in order to get clear images of it, I had to put a piece of translucent paper over it. This will, however, not be a problem in the final design because the laser that's going to be used is going to be incredibly powerful, and so it's going to be bright enough. So this is a control system block diagram of my setup. As you can see, it's closed loop for feedback control. In the feedback path, we have a camera which measures the beam position on the beam pointing mirror. This is then used to create an error signal, which is used to control the beam centering mirror. And this service here is added to model the flexure of the optical components in the path of the beam. So although the control system only consisted of 3 elements, interfacing all these elements was a bit of a challenge. So it ended up being a lot more complicated than I'd like it to be. So all of the processing and the implementation of the control algorithm was done in MATLAB. And the camera had to be interfaced through a separate computer for some complicated reasons to do with incompatible hardware and drivers and stuff like that. However, the most tricky part of all this was interfacing the beam centering mirror with the computer, because the beam centering mirror requires an analog voltage in order to control it, which can't be output by the computer. So instead, I had to program a small hobby microcontroller, an Arduino Uno, which some of you in the audience might be familiar with, to generate a pulse width modulation signal, which is like a square wave with a variable duty cycle. I then had to implement a filtering circuit to convert this signal into the right signal to control the BCM. This is a schematic of that filtering circuit. So the first stage is a simple passive low-pass filter, which is used to convert the PWM, which is the black signal here, into a smoothly varying analog voltage, which is the pink signal here. The second stage of the circuit is an amplification and voltage offset stage, which simply serves to shift this voltage down into the right range to control the beam centering mirror. This is an image of the circuit terminal on the breadboard, and there we have the Arduino Uno, and the magical black box which controls the beam centering mirror. And rather surprisingly, it worked, and it worked quite well, so I left it. So now I'm going to start talking about the feedback aspect. So this is an image of the beam pointing mirror as taken by the camera. So you can see the bright laser beam spot in the center there. So the question is, how can we use images such as these to obtain feedback on the alignment of the laser beam with the beam pointing mirror? The easy way to do this is to simply calculate the centroid of the beam, which should locate the center of the beam. So we use this expression up here, where m are the image moments, which are calculated using these expressions, and x and y are the pixel coordinates of the images, and I is the intensity of each pixel. So as you can see from these images, applying the centroid algorithm to the raw images taken by the camera works quite well when the laser beam is towards the center of the image. However, as it moves towards the edge, it begins to drop off in performance. This is due to low intensity noise in the image, which tends to weight the centroid back towards its center. This is obviously problematic because we can't possibly hope to have a good control system if we can't get accurate information from our feedback sensors. So in order to solve this, I implemented a simple thresholding algorithm. This effectively removes the noise from the image. So in the thresholding filter, all we do is we set every pixel below a certain value to 0. So as you can see, the performance of the centroiding algorithm has increased quite dramatically. Alright, so now that I know how to calculate the centroid of the beam and I know how to control the mirror, the last step is to put these two components together and form the control system. However, how do we go from a centroid information into a control signal for the beam centering mirror? An easy way to do this, believe it or not, is to use a mathematical trick from Adaptive Optics. So first off, the tip and tilt of a beam wavefront, like that, actually corresponds to a misalignment of the beam on the beam pointing mirror. So when the laser beam is on the center of the beam pointing mirror, this wavefront is flat, but when it moves off to the side, its wavefronts become tilted. Or we can rethink of my control system as a closed-loop adaptive optics system, which corrects for the tip and tilt. So that's what I've done here. So this is the original control system block diagram for the system. And this is, we're going to rethink it in terms of adaptive optics. So instead of having a reference being the central position of the center of the beam pointing mirror, we think of having a flat wavefront. And over here, we correspondingly have a corrected wavefront as our output. In the feedback path, we think of our camera as a wavefront sensor to measure the tip and tilt of the beam. And in the forward path, for the correction, we think of the beam centering mirror as a deformable mirror, which corrects for the tip and tilt in the beam. However, how do we obtain the information about the tip and tilt from that centroid that we got from the camera? Answering this question becomes simple if we think of the camera as a Shack-Hartman wavefront sensor. These sensors are used to detect the shapes of wavefronts after they've been, These sensors are used to detect the shapes of wavefronts. So they consist of arrays of lenses placed in front of detectors, as shown up here. And each lenslet focuses incoming light into a spot which forms on the detector here. As you can see in this figure down below, if a wavefront has a non-zero tip and tilt, this spot becomes displaced from the center of the image. And it turns out that the tip and tilt of the wavefront is directly proportional to the center of the stop. That is, the tip and tilt of the wavefront is directly proportional to the centroid coordinates. It turns out that this is actually, all this is a camera, and that's what I already have. And so in calculating the centroid of the laser beam, using those images that I took with the camera, I've effectively calculated the tip and tilt. Okay, so I have the tip and tilt. How do I control the beam centering mirror with the tip and tilt? So this is where the math comes in. So as I said before, I have to think of it as a DM with two actuators which correct the tip and tilt. The coefficient matrix C refers to the control signals which are sent to those actuators to produce a desired tip and tilt in the mirror. I can then use this equation here to calculate the required coefficient given a tip and tilt S calculated from the camera, where M is a command matrix, which is a matrix specific to the deformable mirror, which is calculated in the calibration stage. So this is the result after I put these elements together. So what I've done here is I've given the beam non-zero initial displacement from 0, and I've allowed my control loop to run. As you can see, the beam slowly gets dragged back to the center as desired. So it's working. I should also point out here, though, that the control system at the moment is limited to run at about a frequency of 1 Hz. This is due to an integration problem between the camera and the computer, which we hope to fix in the future, because control system running at 1 Hz for this application really isn't that useful. Anyway, I'll move on. So the next step after ascertaining that the system works is to optimize it. A good way to optimize any sort of control system is simply to analyze its transient response. So we want to have a look at the centroid coordinates as a function of time. In particular, we want to look at three parameters of the transient response. We want to look at the overshoot, the rise time, and the settling time. And for an ideal system of this type, we would like all of these three parameters to be minimized. To do this, we can simply adjust the gain in the control loop. So these are some plots of the x and y coordinates of the centroid of the laser beam as a function of time with different gains. So also, by the way, this gain is not normalized. So yeah. So with a relatively low gain of 5, we see no overshoot in the response, and also it's very sluggish, and it takes almost 15 seconds for the beam to be replaced back to the center. This is clearly unideal. As we increase the gain, the system becomes more responsive, but we also start to see slight oscillations in the response. If we increase the gain even further, we see overshoot, and if we increase it too far, the response becomes dominated by these oscillations, and the control system is almost unusable. So after analyzing plots like these, I ascertained that the optimum gain was about 50. Now, this is a fun video that I have. So to test the loop, I added in some artificial disturbances to control signal of the beam centering mirror. And so this video down the bottom shows the response of the control system when there's no control system implemented. Anyway, and up here is with the control system. So so these plots here are of the x coordinates of the centroid as a function of time. So this is the response. And on this diagram here, you can see that the system quite nicely responds. So it gently moves the beam back to the center after every disturbance. Whereas down here, it just displaces and nothing happens. So I was quite happy with this result because I was expecting nothing to work. Yeah, so future developers like to minimize the complexity of the system by performing all of the computation on a single microcontroller. Because as I showed you before, the system is quite complicated and there are multiple computers and yeah. So thinking I might do this on something like Raspberry Pi or BeagleBone or different kinds of Arduino. I also want to increase the frequency of the control system because, as I said before, it's not currently running fast enough for it to be useful. An interesting side note of this work is that a possible application of it is to be implemented as tip tilt correction for amateur telescopes. And I think that's cool because you don't often hear of something as complex as adaptive optics being used for amateur astronomy. Right, thanks for listening, and thanks to all my supervisors and to ANU for running this program. It's been really good.
So we are not surprised that your solution works. Are there any questions from the floor? Huh? Mm-hmm.
So is it possible to adjust the gain so that it rapidly centers in and then fine-tunes as it goes along?
Yes. So at the moment, it's only got a proportional gain in the controller. So if I implemented like a PID or something like that, yeah, it'll probably be able to, we could probably be able to like optimize the response even more. But I've heard it's very complicated to do that in an AO system. So yeah, I'm willing to try it though. Questions?
What sort of update frequency do you think you'll need for real application?
10 Hertz.
10 Hertz.
Yeah, something like that.
So you've done a little bit of modelling just to...
I read a lot of papers of the people that designed this. That's where I got that number from.
Okay, well, no further questions. Thank you very much, Anna.